Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on theory of numbers, lecture number 48, in which I will discuss some theorems and problems on primitive root. Now we prove a theorem. Theorem is if a and m are relatively prime positive integers and if a is a primitive root of m, then integers a square comma a to the power phi m form a reduced residue set modulo m. Now we prove this. Given that a and m are relatively prime positive integers, that is GCD of a and m equal to 1. This is number 1. Also given that a is a primitive root of m. Therefore, order of a modulo m equal to Euler's phi function of m. This is number 2. Implies that a to the power phi m is congruent to 1 modulo m. This is number 3. Since from 1 GCD of a and m equal to 1 implies that GCD of a square and m equal to 1, GCD of a cube and m equal to 1, comma GCD of a to the power phi m and m equal to 1. This is number 4. Therefore, a square a to the power phi m are all relatively prime to m. This is number 5. Let s is greater than 0, less than r, and r is less than equal to phi m. This is number 6. If possible, let a to the power r is congruent to a to the power s modulo m. Implies that r is congruent to s modulo order of a modulo m. We know this formula. Implies that r is congruent to s modulo order of a modulo m is phi m from 2. Using 2. implies that phi m divides r minus s. This is number 7. From 6 and 7 we get that number 7 is not possible because S and R all are less than or equal to phi m, and therefore their difference does not divide phi m. Therefore, our assumption a to the power r is congruent to a to the power s modulo m is wrong. Therefore, a to the power r is not congruent to a to the power s modulo m. For s is greater than 0, less than r, this is less than phi m. That is, no to a square dot 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 a to the power phi m are congruent modulo m to each other. This is number 8. Since a square comma dot 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 a to the power phi m are phi m in numbers, therefore from 5 and 8, here 5, here 8, we get number 1 a square comma dot 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 a to the power phi m all are relatively prime to m. Number 2, no to a square comma dot 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 a to the power phi m are congruent modulo m to each other. Hence, a square comma dot 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 a to the power phi m form a reduced residue system modulo m. Proved. Now we prove another theorem. Theorem is, let GCD of A and M equal to 1 and let A1, A2, comma dot 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 A phi m be positive integers less than m and relatively prime to m. If A is a primitive root of m, then A a square comma dot 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 a to the power phi m are congruent modulo m to a1 a2 comma dot dot a phi m integers in some order. Now we shall prove this. Prove. Since given that GCD of A and M equal to 1, this is number 1, implies that GCD of A to the power K and M equal to 1. This is number 2. Also given that A is a primitive root of M. Therefore, a square comma dot 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 a to the power phi m form a reduced residue system modulo M. Let S is a set containing these integers a square comma dot 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 a to the power phi m. Let this is number 3. Since given that a1 a2 comma dot 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 a phi m are relatively prime to M and they are less than M. Since they are phi m in numbers, therefore a1 a2 comma dot 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 a phi m form a reduced residue system modulo M. Let S1 is a set containing all these integers a1 a2 dot 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 a phi m. Let this is number 4. Since each member of S1 is less than M and S1 is a reduced residue system modulo M. Therefore, if we divide each member of S by M, we get remainders in S1. Therefore, members of S have residue modulo M as members of S1 in some order. Therefore, a square, comma dot 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 a to the power phi m are congruent modulo m to a1 a2 comma dot 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 a phi m. Proved. Now we verify the theorem by particular example. Let a equal to 2 and m equal to 5. Since order of a modulo m equal to order of 2 modulo 5 equal to 4. Since 2 to the power 4 is congruent to 1 modulo 5. This is number 1. Phi m is the Euler's phi function of m equal to phi 5. As 5 is a prime number, therefore phi 5 equal to 5 minus 1 equal to 4. This is number 2. From 1 and 2, we get order of 2 modulo 5 equal to phi 5. Therefore, 2 is a primitive root of 5. Therefore, 2 square, 2 cube, 2 to the power 4 equal to phi 5 form a reduced residue system modulo 5. Let S is a set containing 2 square, 2 cube, 2 to the power 4. Let this is 3, this is 4. Since 1, 2, 3, 4 are relatively prime to 5 and they are less than 5. So they form a reduced residue system modulo 5. Let S1 is a set containing 1, 2, 3, 4. If we divide each member of S by 5, we get remainders 2, 4, this is 8. If we divide 8 by 5, we get remainder 3. And 2 to the power 4 is 16. If we divide 16 by 5, we get remainder 1. These integers are all members of S1, but in some order. Therefore, members of S are congruent modulo 5 to members of S1 in some order. Now we prove a theorem. Let A be a primitive root of integer m. Prove that a to the power k is a primitive root of m if and only if GCD of k and phi m equal to 1. Phi m be the Euler's phi function of m. Now we prove this. Given that a is a primitive root of m, therefore order of a modulo m equal to phi m. This is number 1. Implies that a to the power phi m is congruent to 1 modulo m. This is number 2. And also GCD of a and m equal to 1. This is number 3. Implies that GCD of a to the power k and m equal to 1. This is number 4. If a to the power k is a primitive root of m, double implication, order of a to the power k modulo m equal to phi m. Since when an integer is a primitive root of m, then its order modulo m must be equal to Euler's phi function of m. And double implication, and this equal to order of a modulo m divided by GCD of k and order of a modulo m. This is equal to phi m. Double implication. Since order of a modulo m equal to phi m, phi m by GCD of k and phi m, right side phi m, using 1. Double implication, GCD of k and phi m equal to 1. Here phi m cancel. Proved. Now we prove the theorem. If the positive integer m has a primitive root, then it has total of phi of phi m in congruent roots. Phi m be the Euler's phi function of m. Now we prove this. Let a be a primitive root of m. Therefore, order of a modulo m equal to phi m implies that a to the power phi m is congruent to 1 modulo m. Let this is number 1, this is number 2. Since we know that if a is a primitive root of m, then a square comma dot 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 a to the power phi m form a reduced residue system modulo m. Here no two members of a square a to the power phi m are congruent modulo m. If k is less than equal to phi m and a to the power k is a primitive root of m, then GCD of k and phi m equal to 1. This is number 3. That is, k is relatively prime to phi m, and also k is less than or equal to phi m. Therefore, possible values of k will be, here integer is phi m. We have to find the number of integers relatively prime to phi m and less than equal to phi m. In this case, we use the Euler's phi function. Therefore, possible values of k will be Euler's phi function of phi m. Therefore, possible incongruent primitive roots of m will be Euler's phi function of phi m. Proved. Now we verify the theorem by a particular example. Example. Let A equal to 2 and M equal to 5. Since 5 equal to 4 and order of 2 modulo 5 equal to 4. This is number 1, this is number 2. From 1 and 2, we get order of 2 modulo 5 equal to 5. Therefore, 2 is a primitive root of 5. We know that 2 square 2 cube 2 to the power 4 equal to 5 form a reduced residue system modulo 5. Here indices are 1, 2, 3, 4. If a to the power k is a primitive root of m, then GCD of k and phi m equal to 1 implies that GCD of k and phi m, here phi m means 4 equal to 1. Therefore, possible values of k are here GCD of 1 and 4 is 1, GCD of 2 and 4 is 2, GCD of 3 and 4 is 1, GCD of 4 and 4 is 4. Therefore, possible values of k are 1 and 3. Therefore, a means 2 to the power 1 and 2 to the power 3 are primitive roots. Of 5. These are 2 in numbers. Means we get 2 primitive roots of 5. Now, phi of 5 equal to phi 5 equal to 4, and this equal to phi 2 square, and this equal to 2 square multiply 1 minus half equal to 2 square multiply half equal to 2. That is, number of primitive roots of 5 is 2. So, our theorem is verified. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.